Hello, my name is Kevin. I've been learning about the Tesla turbine since earlier this year, 2020. Here is a picture of the figures in one of Nikola Tesla's turbine patents. I've found studying the patents a really effective way to learn and also as a point of reference when I'm looking at or listening to what other people are doing in their research and development of this technology. Anyways, I want to use a heat pump to bring energy into the working fluid for a Tesla turbine, and that's what I'm going to talk about in this presentation. The two main ideas are that a heat pump is an efficient way to move energy, and also that Tesla turbines are good for utilizing working fluid at relatively low temperatures, which is why heat pumps are an ideal way to bring heat into the turbine working fluid. So I pretty much just said what I have to say, but to elaborate. Firstly, to give some explanation of the process I'm talking about. A thorough description of the way a heat pump operates is outside of the purpose of this presentation, but I've prepared a diagram showing a heat pump doing what I'm talking about, namely cooling something or somewhere and transferring the heat to the working fluid of a Tesla turbine. This diagram takes, for example, the home air conditioner that many people know and utilize. The main difference between this and normal operation of the air conditioner is that the heat picked up in a house would be rejected by transfer to the working fluid for a Tesla turbine rather than to the outside air. Heat pumps are made in a wide variety of designs to suit a wide variety of applications. For example, aquarium water chillers and heat pump pool heaters move heat between air and a liquid. In a water chiller, the objective is to move heat away from the water and into the air. In a pool heater, the objective is to move heat into the water from the air. But designations of removing from or bringing to are relative to direction, and regardless, a heat pump moves heat from one place to another. And the process by which they do this is energy efficient. That's why many home AC units being made today function in heating mode as well as cooling mode. To talk more about what I mean by the process being energy efficient, in well-designed heat pumps, the energy expended to move the heat is less than the amount of heat energy moved. The numbers example shown here is of a hypothetical heat pump that's not even particularly efficient by present standards. I would refer anyone who is interested to the product literature made available by equipment manufacturers to learn more about the energy efficiencies of various heat pumps being produced today. The point is to give numerical representation of net energy gained through the operation of a heat pump. As far as how Tesla turbines are particularly well suited to make use of that net gain of available heat energy. A Tesla turbine can be made to run off of steam produced at temperatures lower than the boiling point of water at atmospheric pressure. So the temperature of water heated by the heat output of a heat pump can be high enough to power a Tesla turbine. And to conclude this presentation with brief mention of some of the implications and my goals related thereto. Heat pumps are already widely in use, and the heat that's moved by heat pumps is often discarded as waste heat. In fact, there are heat pumps running just to remove the heat that's been removed by other heat pumps. Directing the heat towards a Tesla turbine to produce motive power would be a really good thing to make happen. It's my goal to build things that will do that. I hope to be back with more presentations of information and made things. Thank you for listening.